Okay, let's get started for the afternoon session. I hope you guys have a nice lunch over there. And also another refill of the coffee. There's no refill unfortunately today, so just got poured down the last coffee for me. And okay, let me just remind you what we have done for the morning session for the last time. Last slide talked about policy optimality of the base stock. So here we have come to the conclusion that based on the H function's shape, we can maintain the convexity of the cost-to-go function, and then the base stock continues to be optimal for every period. This is an important proof technique, so we're going to revisit this technique once again when we go to the second case. So we have done with this. And we realize that the base stock policy is optimal for every period up to the final horizon. Now let's revisit the same problem with a different approach by the joint estimation and optimization. 이게 너무 큰 것 같은데? Okay, so what is joint estimation and optimization? As I told you before, we are combining the demand estimation and inventory optimization part into one. And those techniques that we are going to consider is DRL, deep reinforcement learning, and also the bandit algorithm. And so these two techniques are a little bit different. So let me go into the detail in the few slides later. So for any problem that we know the optimal policy type, the remaining thing is knowing the structure. Well, when the optimal policy type is unknown, we have no idea about the structure of our action, right? And the problem becomes more complicated. So we need to know the structure and the optimal parameter at the same time. But if we know the structure, then the problem is something like that. So we know that base stock policy is optimal. And the only parameter that we need to find out is S. So this problem goes to a single variable optimization or finding the optimal S value. So one variable optimization problem. And depending on the structure, the best technique we may think of in terms of AI or learning technique is a little bit different. So the first part, probably we need to think about a general deep reinforcement learning approach because we don't know any structure. So we gotta need to know all the specific action set as a whole. But for the second part, what we need to know is just one parameter. So because of that, a more dedicated strategy would be using another technique like a bandit. So depending on the structure of the problem, we can think of two different approaches. So let me go over one by one. So here I will first talk about the reinforcement learning approach for this multi-period newsbender problem. And this approach is based on my paper on 2021, so which is already a few years ago. And this is one of the first paper that applied reinforcement learning for the newsbender type multi-period inventory problem. So let me quickly remind you that in the DRL, we are basically solving dynamic programming, and the dynamic programming in nature has its value function and also the Bellman equation for the optimality. So we already have applied our theta t of x, which is another value function in our problem. Actually, the value function calculation numerically can be done numerically by just repeating the values inside of it and repeat once again in order to obtain by one specific policy the value function of every state. This can be obtained by repeating this Bellman equation structure by using another state value here for all other state value here, and the value, the state that we want to obtain can be expressed as the value function of other states. And if you repeat the previous value function formulation with Vk, our new Vk plus 1 is obtained by repeating all the expected value calculation of different states. And this is what we imply for the Bellman equation iteratively. Well, once we obtain this value function, then we are able to calculate this Q function of for given policy, and the policy of the Q, the action is obtained by maximizing this Q function of SA, and then we will obtain the pi function, and the pi function will give you another action value function at the same time. So either we can directly work with the value function, or we can work with action and value function. As I said, sometimes if we can directly obtain value function without the Q action values function, then it'd be a little bit easy problem. Then we can directly go there. Sometimes it's kind of too complex to obtain this value function, or if we don't know the policy type exactly, then we may need to go to the action state function Q, which will automatically derive you the policy set in addition. Yeah. So if your problem knows the policy type, you can directly go to the value function. If you're not clear about what policy that you want to try, then you can construct numerically a new policy based on this action value function. So how to obtain this action value function and how this repetition goes well, I'm gonna just skip the detail, but basically this is the same as solving dynamic programming as a whole. So this kind of policy iteration is quite famous, a famous numerical technique that you can verify the value function, and eventually you can improve your policy, and then it is guaranteed that you can obtain the optimal policy based on this iteration. But still, there are certain challenges in it. Okay. First, this kind of dynamic programming is based on this equation. So you gotta need to know every element of this in order to verify this value function. So even if it's an action value function or value function, you need to know at least this part and this part. The first part is the policy, and maybe you can avoid this part by using action and value function as Q. However, this kind of probability part is something that should not be missing. So in every iteration of dynamic programming, you need to know the probability or the transition from one state to the other. In terms of the inventory, this is the following. If you start with inventory 100 in your warehouse, you need to know exact probability that your next period warehouse inventory becomes 120 or 110. So essentially, this means that you need to know the distribution of the demand, meaning that you have to know the probability that your customer demand will be either 20, 30, 40, 50, and so on. This is quite natural. So if you happen to know, or if you start with the distribution assumption, or if you happen to know the distribution of customer demand, then one natural approach for solving your dynamic programming and obtaining the optimal order quantity is obviously using this dynamic programming. However, I told you that sometimes we do not want to resort to this kind of transition probability. And instead, sometimes we want to work with a observed numbers of the customer demand data instead of having some assumption or distribution assumption on the customer demand. If that occurs, then we gotta replace this one with some samples of the customer demand observation. And when we need to work with its kind of observation instead of a dedicated probability, a complete knowledge of the probability. Instead, if you want to work with a limited number of customer demand observation, then you gotta need to develop a new technique, which we call by a reinforcement learning. So basically, when we talk about RL, typically we are assuming that this kind of probability structure is not known, or it doesn't have to be known. If it's known, it's good. But it doesn't assume that every time we know a complete transition probabilities. Instead, we gotta trace the sample. So that's the basic notion. Instead of taking into account of all the probability, in other words, all the potential events that can occur with a certain exact measure of the probability, we want to know what happened in past with our limited knowledge about the transitions that we have observed. So that's a basic idea. Instead of taking the probability measure, we are now taking a certain observation ratio. So for A position, we got an observation that it actually goes to B or C. Then based on the B and C realization, we assign a certain probability, a temporary probability. So then we can update those probabilities when we have more observations. So that's the basic idea of the reinforcement learning. So the good thing about the RL, reinforcement learning, is we don't need to know the transition probability exactly. And at the cost of that, because of that, then we gotta run this dynamic programming or the learning approach with quite a lot of observation, far more observations than you can think of. So sometimes you may need millions of observations or even trillions of observations. So the more we observe data, the better our programming is. So the objective of this reinforcement learning technique is how to reduce the computation for learning. In other words, in order to know the transition, without knowing the transition exactly, how we can speed up our estimation of the transitions based on our limited knowledge on the customer data. But how can make it happen? It's not easy because we have no idea what the transition would be. So here, what we are using is, since basically in this paper, we know that this is an inventory problem, right? So instead of having a naive observation, we have an idea that if we start with this kind of inventory position with some kind of product in the warehouse, in the next time period, probably you have a better idea about the potential distribution based on this starting point and observed demand. So this means that not only just observing the result as is, we got an idea because we know how the use vendor and multi-period inventory problem works a little bit. So let's just use our knowledge as much as possible. Then, in addition to knowing a little bit more about the potential transitions, we also know that certain decisions, in other words, certain inventory position or the order quantity, certain set of order quantity is good, whereas a certain set of order quantity is bad. We can actually specify a area of the potentially good order quantities based on our previous knowledge on inventory theory. Okay. So this is very helpful because basically this will reduce the number of samples that we need for our learning and also speed up our policy as well, because not even knowing the policy exactly, maybe we can teach the reinforcement learning a little bit with our policy structure that is known to be optimal for the similar problem, and then it can speed up our learning far better than starting from the scratch, starting from the nothing. Okay, so that's a two basic idea that we want to employ. So here we are just assuming we are just solving an MDP problem for a multi-period newspaper problem or infinite horizon newspaper problem, which is essentially the same. Now we define the pipeline inventory vector, which is close to on order. Okay, something that is coming but has not arrived yet. And also for the state vector, we have the initial inventory position plus something that is coming. So on orders. And my action is the order quantity for this time period. This will also affect some order quantity that is coming in the next period. Not exactly the next period, but for a certain period later, depending on the lead time, because the order quantity that I have made today may not come right now. It may come a little bit later than a certain period. So we need to specify this state vector, and then our action can be specified as a function of the state. So if we happen to have a certain number of initial inventory, and if we happen to have a certain numbers that are coming next period, then we can make the best decision by making a lot of experiments. And it's clear that this kind of decision depends on the two states. However, the problem is, this is initial inventory, so it may have a certain range of the numbers. This is also another vector. It actually has a lot of dimensions because it includes all the orders that are coming next period, next second, third, fourth, fifth times later on. So it includes all the different pipelines of the orders that are coming right after my current time period. So the problem is it has too many dimensions. And dimension is very important in any dynamic programming because it will make your number of experiments much more and more. So if you happen to have two states, probably your state, the number of experiments you need may be 100 or even thousands or even 10,000 times more. So this is what we commonly call by curves of dimensionality, right? In dynamic programming. So we should not have any state larger and larger. Instead, we want to reduce the dimension of the state as much as possible if we can do it. So can we use our knowledge on the inventory to reduce the state of this problem? Fortunately, yes, because in order to make the decision of current period, what we need to know is what we had before and what is coming next. So instead of knowing all the different numbers one by one, it's actually good to know the summation of two number inventory position of last time period, my starting point, plus inventory of T minus L, whose order is coming next time. Then it suffices for me to make inventory decision based on my knowledge on the lead time, multi-period new spender type of the inventory problem. So this kind of technique is quite typical in any of the reinforcement learning technique. So by just using this instead of this, we can reduce the dimension of the state a lot. Then it's good for learning all those policies. So the state vector reduces significantly by using this inventory related domain knowledge. So that's one technique. And there's going to be another technique in our calculation. So by just applying all the things, now we are ready to apply everything. And this is the algorithm. So we have used the summation of those two values instead of the individual variables in our IP because this is the only value that matters for our inventory decision. And we've also focused on learning the decision of the Q equals 0 by making it non-negative. Because in our inventory decision, we don't need to think about any negative value as my decision because we are not reducing our inventory position from now to the lower position at all. So we cannot reduce the inventory position by ordering something. So we only need to take care of the positive part. And also the zero order quantity sometimes is very important because do you remember our base stock policy? Many part of my base stock policy remains ordering nothing. When does it occur? So when, let's say that I have my S star, right? And if my starting position is already higher than S star, I'm not doing anything. In that case, what is my optimal order quantity? 0. So if we happen to implement this base stock policy, we gotta have a lot of zero ordering cases whenever our position is higher than the optimal one. So we have to be very careful in this Q equals 0 instead of Q equals negative. We don't have to consider it at all, but we need to be careful because most likely we will see a lot of Q equals 0 case. So we need to focus on learning this decision, and also we have to set the decision space as a non-negative one. And 0 can be separately studied because this can be regarded as the case where your inventory is already higher than the optimal inventory position. Also, we can reduce the space effectively by thinking about a effective boundary region. So in terms of the maximum backorder, actually maximum backorder can be infinite, but maybe we can reduce the number of a maximum backorder in a reasonable number. Then by reducing it, it can be a little bit easier to implement this problem. And also we can think of an upper bound of the order quantity, which is actually not existing in the original problem, but by implementing this a reasonable upper bound of the order quantity, maybe we can reduce the search space and then make our problem a little bit tractable. So with all these techniques, the algorithm comes here. So basically this is a DDPG algorithm and deep deterministic policy gradient algorithm. But since we have added some of the inventory related features, like the following here, we call it as an inventory-based DDPG. So which is IDDPG in short term. So let's compare the result. So by just naively applying DDPG, we have this kind of cost So the cost gap from the base stock is follows here. And then if you compare it with the cost gap compared to the base stock, you see that most of the numbers here are quite stable and low compared to the DDPG number, especially when the lead time becomes quite long and demand volatility. No. Shortage cost is high, then the DDPG as a naive approach cannot guarantee a good performance. It's kind of not stable. However, by just reducing the space and also reducing the spaces and the action space that we can think of, this IDDPG effectively just shows a better performance, which is substantially better in terms of variability. So here this graph just shows that not only this optimality gap is good, during the training time, our algorithm is kind of a monotonic decrease in the optimality gap. So meaning that it's monotonically getting better and better, whereas the naive DDPG approach, because it has a exploration part here, so sometimes it's kind of going off and off. And even in the worst case, it can actually go to the wrong direction and then the cost actually goes up. So this kind of unstable behavior can be avoided by just using all of the domain knowledge of the inventory related parts. So here what I want to say is by just mixing your deep domain knowledge of the inventory model and also the deep reinforcement learning approach, when it combined together, then the real synergy occurs. So you have to study both domains carefully in order to produce a meaningful research outcome. So I don't know whether I can say that in public, but studying those two fields at the same time is very hard. But that's why you have some opportunity, because studying both fields at the same time is quite difficult. If you happen to do that as much as you can, then you have a chance to advance this field. So that can be another opportunity. Yep. There's no assumption in the demand distribution. I think we just see the numbers. So it's a kind of data driven. So just like our second worksheet in Excel, we just get the numbers of the customer demand observation. But naturally, that's a typical approach for the DRL, which does not need any distribution assumption at all. Yep. Thank you for your question. So here, I just get the recent paper on MSOM regarding the DRL. And here in this paper, they have just applied A3C, another DRL approach, without many modifications. They just apply it as is to various problems, like a multi-period inventory problem with lost sales, and also dual sourcing problem. So these are known to be quite difficult to solve. And we happen to know the structure of the best policy. So because of that, analytically, we may have a chance to optimize it and get the result. So here, the gray one is the best analytical result that we obtained so far from any theory or paper or the specific problem. So they are really good, but the problem is these approach are only valid for a certain type of the problem. So if your problem setup changes a little bit, your algorithm stops holding. So you need to change your algorithm. But the A3C based DRL algorithm works quite universally. So they find that the performance of their A3C based DRL is quite close to what is known to be optimal so far. This is already 1 or 2 years ago. So I don't know what is going to happen this year. Probably their performance, the DRL performance may be better and better, right? But in order to increase the performance of this DRL, I think just as we did before in our previous paper, we have to combine our specific domain knowledge in order to speed up. So it's not bad, but this is not the only solution to have more hardware. For example, better GPU, more number of computer servers. That will also help because that will speed up our computation, right? But also by combining our knowledge on the inventory domain knowledge, we can reduce the space, which equivalently can be reducing a lot of GPUs, a lot of servers. So there are some chances that you can still contribute to this kind of the problem without having the most best hardware on the earth. Yeah. Still, I have to confess that you gotta have a good hardware to implement this one. So at some point of time, you will find that hardware can be your bottleneck in your research, which rarely occurs in any OR type of research. So far, traditionally, the bottleneck is your brain. But here now you have a new bottleneck in terms of hardware, but there is a way to overcome certain restriction on the hardware. And also you can find external resources like a cloud computing with some better GPUs, but per time you can just pay for it, right? I think POSTECH, you can also gain access to kind of good computing centers like that. So this can be another way. So combining your knowledge, you have another chance for making big contributions. So that's all for the base stock policy. But base stock policy is one of the simplest policy or the simplest setting without any, fixed cost. So this only applies for 무료 배송, 무배 case. But most of the problem has a certain types of the fixed cost, especially if you think about any B2B transaction. So if you're a manufacturer and you are delivering your parts to the retail company or any warehouses, what are we using? Large truck, yes, or small truck, or train, or even you can even use the ship. Sometimes you're exporting car, and it needs a specialized ship to move the cars from here to the US, to the Asia, or in other places. So then you can think of that the fixed cost actually matters a lot, especially for B2B transactions. So obviously, S base stock policy is not optimal for most of those cases. Then, if we have a fixed cost, how the chain problem changes? Now we think of a fixed cost K that occurs regardless of our order quantity. And every time we place new order, let's say that this K cost occurs. So we can think of a new policy type. Another famous policy type is SS. So the structure is the following. Each time we observe the current position. And if my current position is less than S, small s, sorry for my handwriting. In my hand, small s and large s looks the same. But that's the same for the printed one, right? So it's quite bad because this guy who implemented SS used the same character, S and S. I don't know why, because it looks exactly the same. So be careful. When I use small s, it's really small. When I use big S, it's capital S, okay? So if your position is less than small s, then your order must be up to large S. That's how it works. Large S. So you basically have two parameters, small s, large S. So let's say that why this kind of structure is necessary. So we can just solve one period problem. So I'm not repeating it for the whole multi-period case, but now the difference is now we consider this kind of new cost. What is it? This delta of x function is 1 if your x is, yes, direct delta. It's a positive and it's a 0 otherwise. Okay. So why does it matter? Why does it matter? Because your new position y is strictly higher than x, then you are making a positive number of orders. And that's the only case where you have to pay k. So it's a k times direct delta of y minus x, and everything else is the same. So it looks like quite simple adaptation, simple modification. So you may hope that probably the same structure would work. But actually the impact of such k is quite high. So your y is S star that minimizes, okay. We also assume the same S star that minimizes my h. So our h would be the same. But let me just show why this is not a simple problem. So think about hy at just before, and now think of this case. Let's say that my y is here. And this is my x. So obviously, when we only think about base stock, where should we go? We should go to this part. By the way, this is large S. So now I intentionally make it large, right? We have to go to this part. But actually now we have to pay k. So we are never be able to go to this position. Instead, we are going up a little bit by k. So this will give us a new region like that. So for example, if you are here, then still it's good to go to this, because even if your position goes up a little bit here, then that's your cost. But anyway, this is better than your initial. However, if you happen to be here, now this is the new case that have never existed. If you are here, then if you happen to go here, then you have to pay the k cost, and then your resulting cost is actually higher than your initial position, right? So that's why you kind of more conservative in making an order due to this cost. So we have to divide the space another before and after this k, right? So that's where the small star exists. So we are only making orders when our position is less than or left-hand side of this small s. In the middle of those two, initially it's good to move, but now it's not good, so you have to stop. So making order, if you are left side of this, and also if you are making order, then you are making an order up to this. So that's what this large S means. So anyway, so small s divide the space into the order area and non-ordering area. Large S just determines how, if you make an order, what is your objective. So simplifying all those decisions, we have this. If your position is less than S, then order up to big S. That's the type of the structure of this policy. So what is the definition of my H small s star? H small s star satisfies SH of large s star plus K. So this is the place or the equation that we are satisfying with a small s star. So we want to know whether this kind of relationship continues. So let me draw a figure and just show you why this is quite complex. Our H with the minimum in the base stock case, we had a figure like that. Do you remember? So it remains convex. So this structure continues. So if theta t plus 1 is convex, theta t is still convex. Now we go back to SS. So you start from the same convex structure. And I know that you have to make an order here, depending on your position here, and the difference is K. So by just applying the minimum, then the resulting figure is not this, but what? So what are we doing up to this part? Doing nothing. So nothing. So what are we doing from here? Order, make an order, right? Make an order, but you also have to pay for the purchase cost. So the resulting figure is either this or this. But anyway, it doesn't matter. Anyway, what is important is there is a shape like that. Okay, so now I want to ask you the question. Is this convex? It's an easy problem, yeah. Why isn't it convex? Convex? What's the definition of convex? You pick 2 points, you draw a line, the line should be always above the graph. So where does it break? Here. You pick the 2 point, you draw a line, now it's below the graph. Yes. So it's not convex anymore. It's not convex, meaning that you cannot continue your convex assumption. So theta plus t plus 1 convex, theta t convex. So this does not hold anymore. But it's not convex, but don't you see any structure in it? It has a specific structure. But it is not just convex. That doesn't mean that it's quite irregular. It actually has quite certain type of structure, convex plus some line, either decreasing or flat. So it's unfair that saying that it's not convex, so we cannot do anything. So for several years, for many years, people are trying to characterize. So what I meant by characterizing is people want to define a structure that works just for that and prove that the same structure remains holding for t, theta t minus 1, theta t minus 2, something like that. So we want to make sure that a certain structure type holds, continue to hold for different time periods, which is not exactly convex, but a variant of convex. So that's why we implement a K convexity as a special structure. Have you heard about K convexity structure? Some of you probably not. Because as far as I know, K convexity is one of the few concepts that's not coming from mathematics. In other words, we know that convexity, concavity, first order condition, most of the techniques are already there in the mathematics, right? But this kind of K convexity is a special structure that are only observed for certain types of the inventory problem. So it's derived or developed from inventory context. Okay. So what's the meaning of the K-convex? It's quite complex. The K-convex definition is for any X and for any A and B positive, we have X, X minus X plus A, and X minus B, we have 3 points. For any 3 points, we have the following, Fx plus this. This is just a slope of any 2 points, and X plus A plus K. So when K equals 0, this just to coincide with the regular convexity definition, but we are extending it a little bit. So maybe you can simply regard it as a slight relaxation of convexity. Up to how much? Up to K. But this is a little bit stronger than that because our structure is quite special because we have small s and left of the small s, we have a certain, what is it? The line structure. Right after small s, we have a convex structure. So this is not just a simple convex function. So this kind of definition, although it does not look like describing this complex structure completely, actually this works quite well. So I'm just skipping the detailed proof of this structure, but please believe me that it turns out to be very useful. Actually, I can derive the useful property, something like that. For example, if this works, I can prove that for number one area, it's monotonically decreasing. Non-increasing. And for number two, it's decreasing. For number three, it's increasing. However, even if it decreases, the difference between the two is always less than K. Why is it important for the number three part? Even if it's not just increasing, even if it can sometimes decrease, the difference of the peak, those two peaks is less than K. If it's less than K, then it's not good to make any order at that time because you cannot reduce your cost more than K, right? So for me, in order for me to make any ordering decision after that, I have to make any difference larger than K because the K is the cost that I have to incur when I make an order. But this is guaranteed that you cannot make any cost reduction higher than K. So there is no reason for you to make any order in region 3. So this kind of 1 to 3 result comes out only from this definition, so which is amazing. So here's the plot for the K convexity structure. Well, we are basically looking for the slope that comes from the 2 points and the slope of this and the other point, the difference is always less than K. So that's the definition of the K convexity. Obviously quite strange than our usual convex definition. And I can say those properties and then I can prove that when this zeta t plus 1 is K convex, H is K convex, and then if it's K convex, SNS, SS policy is optimal, and more importantly, theta T, which is defined by this. I'm sorry. So my theta t x is mean y greater than x, direct delta y minus x plus g y plus gamma e t plus 1 y minus d minus cx. So this theta continues to be what? K convex. So where do we start? Start from here. So I'm saying that this is K convex. And this is convex. And summation of convex and K convex results in K convex. Just because our convex can be interpreted as zero convex. Yes. So summing of those two, we have another K convex. And this is just direct delta. And we can say that still we have K convexity holding. So even for the minimum, I have this kind of structure, and the minimum of this remains K convex. So here is a quite famous proof of SS policy. So for this type of a special problem, multi-period, lead time, doesn't matter. But if we only have a ordering cost that are fixed and that are incurring regardless of our order quantity, we know that SS type policy is optimal. Here's the figure. But still, it's good to know that SS policy is optimal. Then the remaining task is find out 2S, right? Actually, for any finite horizon problem from 1 to t, you gotta have ST and large ST independently for each time period. So you gotta still have to have a lot of calculations to find out each S and S parameters for each period. So, but anyway, even for a single period, calculation of small s and large s is not trivial. Yep. Because just because this calculation is not easy at all. This is the same for calculating base stock S. So by using this dynamic programming function, we have a specialized form y minus d, which is a bit more complicated than y of d. Okay, sorry. Theta of d. So if it's just the theta of d, then the range of the random variable, random customer demand, and the range of the space that we have to consider for the function would be the same. But here we are thinking of y minus d. So our range of y and our range of d will make a new space of y minus d. So it's kind of hard to apply this one, not just for single s, but for small s and large s pair. So you have to make a second grid. So if you are making a grid approach of small s and large s, it takes a lot more time to determine both parameters at the same time. So calculation of the expected cost goal is significantly more involved, and often they are specific to time period 2t. So you have to calculate them in each period. And S and S depends on each other. In other words, you have to think of those pairs at one time, so each time, because you cannot calculate one alone by separating this problem into two. So your S and S should be combined each other in order to obtain the best performance. So making it harder to calculate for multiple retailers. If you happen to have multiple retailers with each S and S for retailer 1, S and S for retailer 2, and so on, then this keeps more and more complicated. So this is not an easy problem at this moment, even if you know the structure. So, have you seen this paper? So, this paper is written by your Professor 최 동구 교수님. He wrote a nice paper on the reinforcement learning, especially for SCS policy. This is for a specific problem for a complex form of fixed cost. And they are thinking of a multiple products. So combining the multiple products, the fixed cost depends on the product portfolio and the quantity and so on. So it's quite complex problem. And it's a kind of variant of SS policy. So in the middle, they have another C type, which is actually well known. And then they apply the reinforcement learning technique to derive to how to easily calculate those parameters based on the structure of S, C, and S. So basically, you have to find out three different parameters in this problem. So I was thinking to ask him for introducing this result. If you want to know more, maybe you can talk to him, not to me. Yeah. Another interesting paper. What we are focusing on is actually a little bit different technique. So far, we have introduced reinforcement learning technique, but we have seen it that finding small s and large s is a kind of knowing the best combination of all the grid space of s and s, right? So probably instead of taking a more complex reinforcement learning, maybe a bit more simpler bandit can work. So have you heard about bandit technique before? So this bandit is designed for this kind of, what is it? The casino slot machine. So let me go back to this problem. So basically you go to the casino and you have a different number of slot machines, and you gotta know which machine has the highest winning probability. Now you don't know, but the probability itself is already fixed. So what you are doing is you have some experiment by inserting some coins for each machine, and by using 100 of your limited coins, you gotta know which machine may have the highest winning probability from your experiment. Does it have some similarity with our SS parameter optimization? Kind of, because this kind of slot machine can be some values of, for example, large S. So you gotta know which value of your S becomes the optimal. That's the similarity, but this is not the same problem. Why isn't it the same problem? So think of the multi-period inventory problem. In this setting, if you run one machine, then your result is not carrying over to the next time period. In other words, if you do another experiment, your result of the previous one doesn't matter, doesn't have any impact on your current position. However, if you run an inventory problem, your decision on this period of S equals 100 would impact your next period inventory position. So they are interrelated. So you cannot separate it as an independent problem. So because of that, you have to be very careful in finding out the period that you have to take care for this kind of bandit-based inventory optimization. So this is one important feature that we need to take care of. However, there is some similarity. So if you happen to implement it in a smart way, probably you can implement a nice algorithm. This was lunch break. I made a wrong estimation, so I have to adjust my forecast. But anyway, it's already 18, so let's just have another break. Thank you.